Okay, hello folks. This is the video tutorial for homework number 2, which goes with lab 51. Okay, there are two problems here, and problem 1 is a ring like that, and it's pinned at the top, and the middle of it, the middle bottom portion of it is being pulled down by a force, but we don't know what that force is, except that we know that the displacement of that point associated with the force shown is 0.01 inch. This is problem 1, but that's not the one that you have to submit. So I'm going to do problem number 2 first, and then come back and do problem number 1. How about that? Problem number 2, the one that you have to submit, is a frame structure like that. The coordinates are given, dimensions are given, so that you can do the problem. It has the structure. This structure has a cross section, which is it's a radius. It's a circle of radius. Let me see now. Circle of radius 0.25 inches. Okay. So 6 inches, 6 inches, 3, and the cross-sectional radius is 0.25. Now, when you look at this problem, it says use the most appropriate element to solve the problem. The most appropriate problem is going to be beam problem. Do not make this three-dimensional object and model it with solid elements. That's a big deduction, a deduction of marks. Okay. Now, the other thing is that it says use symmetry to reduce the model if applicable. So clamped, the geometry is symmetric about that point, and this point is being pulled down. I hope you agree that anything that happens on the right is the same as what happens on the left. So you have two choices. You can make half of this because you know that this is going to be the geometry that you're going to be modeling, or you can model the whole thing and then cut it. I'm not going to go that route. This is a simple problem. So I'm going to create this piece, okay, and then solve the problem. Now, there's two approaches with this type of problem that you can have, and we talked about this thing in class. You can either sketch this thing in a sketch, in other words, draw this thing in a sketch. You can do that. You can draw it as a sketch and then join it and then move and mesh it. The other option is to draw three lines like this, 3 lines. That's not in a sketch necessarily. Just you create 4 points, these corner points, you create them, and then create line between. So you get 3 separate lines and then join it, and then proceed with the rest of the problem. Bottom line, either create a sketch and join it, or create 3 lines, join it, and then move on. So for this problem, let me do it as a, for this problem, let me do it as a uh, 3 lines. How about that? I make 3 lines, and join them together. The first problem, when I'm going to do it, I draw it as a sketch in space, not a sketch, as a wireframe in space. Okay, so let's move on. That's the problem that we are doing. I'm going to create 4 points, 1, 2, 3, 4, and create the 3 lines in between. So Goku Katia, start with a part file. Immediately save it. File, save management, save as, desktop, new folder. I'll call it uh, homework 2, lab 52, problem 2. Okay, you say all right, and I'm going to put it in there. And the name, I'm going to call it, how was saying that, used wireframe, not sketch. Okay. Oh, remember, if you have to submit this thing as a homework, and you do, let's do it the right way. Your ID number 123456789. Your ID number dash Timoshenko. Timoshenko. This is your last name, and we call it problem 2. I'll call it lab 2. Lab. I'll call it homework 2. Homework 2. Problem 2. How about that? Problem 2. And remember, I decided to do it with wireframe. So we say OK, and we say OK, and we create 3 points. I'm going to be in wireframe and surface design. OK, you don't need. You can also do it in part. You can also do it in part design if you want, but right now I'm in generative shape design. That's what I said. That's what I meant. So let's start the point. 1 point, coordinate 0, 0, 0 right there. Another point which is 3 inches to the right. Another point which is 6 inches up. And another point which is again 3 inches to the right of this, which is 6 inches altogether. And this is it. So we created our 3 points. Let's create 3 lines. Line 1 goes from here to here. And then from here, this is line 2, from here to here. And from here to there. And we say OK, and when you're done, we say cancel. And remember, I will join these. If I don't join it later on, when I mesh these, I have to do it one by one. And when I do it one by one, over here, you have a node number from this side and a node number from that side, which are different. Okay? Now, it is possible to arrange things so that the node number from this side and that side become merged. However, you cannot do it in the generative structure analysis. You have to do it advanced meshing tools, and I'm trying to avoid advanced meshing tools for you in this course, unless some very basic stuff that I'm going to show you. Okay? If you want to have common nodes between these two lines at this location, you need to join it. Okay, so let's do the join. Here's the join operation. You select this line and that line and that line and say OK. And it's a single item that is joined together right there. When I mesh it, the entire thing is going to get meshed. It's not going to be individual lines. The entire thing is going to get meshed, and there's going to be a merged node at this corner point. Now, we don't need these points. Let me hide them. So this all the way down there, we're going to hide them. And there's a reason, because if you don't hide it, sometimes you accidentally put a force or a clamp on a point, and you don't mean it. You mean it at the vertex. See, there's a difference between this location. This is not that point. This is the vertex of that line, okay? And if you put a force or a clamp, for example, on a point, CATIA will not run. All right, let's go ahead and do that. We're done here. We're going to go to a generative structure analysis. CATIA does not see a solid object, therefore it's not going to mesh it. We're still doing a static problem. So here's the beam element. See that? This is the one that you have already used. And CATIA, as soon as it sees a solid object there, it's going to use this. But there is no solid object. So we're going to use beam element right there. And you select this join, and everything lights up. And let's say that the size we're going to specify to be, I don't know, 0.1. So the element size, the length of each element is 0.1. Okay? And we say OK, and it's done. Look, the mesh has been created. And if right there, you can see that. Put the cursor there, right-click mesh visualization, and it's done. If you get close, you see that? So these are the, let me get closer here. So this is element number, I don't know, maybe, let's make it like that. This is element number, I can't read it, 91, which goes between node 4 and 93. This is element number 92. It goes between node 93 and 94, etc. If you get to this corner, this is element number 120, goes between between nodes 121 and 3, and you go from the other side, it's still the same thing. It's node 3. That's because we joined it. Okay? The elements are created. There is nothing fancy there. It's nothing, exotic. Just deactivate it. All right. Now we're going to say what kind of a cross section we have. The problem says the cross section of this is a circle of radius 0.25. So you go to 1D property. This is for beam property. See 1D property. You click on it. You select first of all cylindrical beam cross section, and you click on the wrench, and you put 0.25 in it. 0.25. The radius. Let's make sure. The radius was 0.25. Oh, diameter is 0.25. Okay, so let's change this thing to diameter. Uh, Radius of 0.125. How about that? 0.125. We say okay, and we say okay. Oh, it says the support. The support is that joint. So what it does, it creates beams with circular cross section on all of these with the same radius 0.25. Now, I'm sure some of you will ask, what is this radius is different from the radius over there? Well, there are things you can do, but not right now, not in this problem. You say, okay. Uh, I meant to select not the edge. I meant to select the join. I did that. 1D property. Did I specify material on this? Oh, that's what it was. That's why it didn't do it. It was missing. Cancel. So that you don't get confused, let me do the following. Delete this. I don't want you to get confused. Apply material. That's what it was not closing it. I could have done it at that point, but right here, metal on the part. And those are properties of steel, I think. I'll take the default properties of steel. It says steel. Yeah. Is it steel? Yeah, steel. So there, we say okay. Now back to generative structure analysis. I could have fixed the issue there, but I decided not to confuse you. So I went there, say okay, and mesh it right there. Same numbers, mesh is created. Now we go and do 1D property. You select the thing, this thing, and material is picked. Cross section is this cross section of radius is 0.125. Say okay. Now I can close it. Now remember, before I could not close it because I didn't know what the material was. I could have defined it there, but I rather not. That's why I killed that analysis and went to the part, applied material, and returned to it. So very good. Now this end is clamped. Clamped is simple, right there. Now, what that means is that 6 degrees of freedom are fixed. Now, if question may be, and people asked me about this thing before, could I have done it like this? Could I have done user-defined restraint? All of these checked. Yes, you can do that. I could have selected this and would have the same effect. But clamp will automatically do all 6 for you. Now, the other thing is that this point is in the plane of symmetry zx. See, if you look at zx, this end, this vertex is in that plane. Now we know the rule for applying symmetry restraint here. You can't use surface slider and things like that for beams. So you go to user-defined restraint. Let's uncheck that. This is the point. This is the point. It's in the xz plane, therefore it does not move in the direction y. If it's in xz, it does not go left or right. So uh, this is fixed, and rotations are exactly the opposite. Rotations are exactly the opposite. If this is fixed, corresponding rotation is free. If these displacements are free, the corresponding rotations are fixed. That imposes the what is it called? The symmetry. Okay. Just to remind you of this, let me go there. You don't have to do it, but I will do it on purpose. This is symmetry. Properties, symmetry. Let's say symmetry condition. symmetry condition. Okay, good. Now, I also want to push this thing down by some amount. Push it down by some amount, I have to first make sure it is zero by that amount, by zero amount. So you click on it, and just so that we don't screw this up. So again, you select this point, and you say no displacement in direction Z because I want to change it. If these things are bothering you, hide it right there. You see that? No displacement in direction Z, and just so that we see what this is going, this is for pushing it down, for pushing down or up, pushing. Okay, how about that? You say okay. Now we can go and change this. So you go to enforce displacement, you select this, you said, oh, I didn't mean it to be 0, I want it to be 0.01 with a negative sign, because that's what the problem says. I think it says 0.01. Yeah, 0.01 inch by a negative value. Okay. You say okay, all right, and this is it. So let's save the analysis. File, save management, analysis is here, save as. Uh, uh, so what did we call this thing? So we call this thing as 1, 2, 3, 4, 5, 6, 3, 4, 5, 6, 7, 8, 9. This is your user ID. Timoshenko, that's your last name. You wish, or I wish. Timoshenko. And this is homework 2. I think it was problem 2. This is the one to be submitted, right? Problem 2. Okay, very good. And say okay. Very good. Now, again, be careful. If you had not hidden those points and you put this class accidentally on the point here, or these conditions accidentally at the first point that are created, CATIA will not run and bomb out, okay? So now we're gonna run it. Say okay. It's done. Look at the deformation. Does it look right? Well, put it from the front view because it's easier to judge right there. Okay. And let me animate it right there. That makes sense. You see this? It goes down, but this middle point stays on that vertical line. Okay. Here, look. If I had not used symmetry, this would have gone to the left or would have gone to the right, possibly. Okay. It would have gone to the right if there was no symmetry condition here. Okay. Now, you want to see the numbers? Click on the displacement, 0.01 inch. Remember, I applied 0.01 inch here. Double click on it, make it average ISO. That's better. Okay. So these are the actual displacements, contour. Of course, over here it's 0. Over here is maximum because I did apply 0.01 displacement down. Okay. And because there is no displacement to the left or to the right, and in the plane, the vector component, a vector magnitude becomes exactly 0.001. Okay. Now, if you want to know what is the stress distribution, you're out of luck, because remember, in CATIA, it's horrible for plotting stresses in mesh in beam elements. It won't let you plot the von Mises stress. The only thing that you can plot is the axial stress, principal stress, which is axial stress, and it's totally useless. Okay, you can plot it, and you can see what happens here. You can see that all you get is the component of stress in the axis direction. Well, we get it, but that's totally useless. Now, the reason that you cannot plot the von Mises stress, I hope is obvious to some of you. Let me get rid of that first of all. I want to get my displacement plot back. Here, displacement plot. Now, the reason it won't let you plot the von Mises stress, I want you to go back to the stress analysis course that you took, or the, you know, end of deformable bodies stress analysis course that you took. Notice that von Mises stress requires this 6 components of stress. For a beam, the question is, at a cross-section location, where do you want to take your your point where the component of stress are calculated. Some packages allow you to tell the software at what location on the cross section you want to plot the von Mises stress, and then you get some information. In CATIA, it won't let you do that because its beam capability is very limited. Okay, last part of the problem is this. How much force is needed to cause that displacement? Let me right click here, deactivate that. Okay, so remember how you get the force? You go to the sensor, right click, create the resultant sensor, reaction sensor, and for the uh, it's expecting you to select the restraint. So you go to pushing down, see that? Pushing down, pushing down, pushing down, and update. And it will tell you you need 0.6, almost 0.7 pounds to push it down. Wrong, because that 0.7, is only for half of the beam. The actual force that is needed to cause this deformation is double of that amount. In other words, uh, almost 1.4 pound. This is why we left a box here. This is coming from an old test, okay, which it says write your answer here. You better write 1.4 or 2 times 0.69 to get the full mark for that, okay? All right. So that takes care of the second problem. Now I want to go to this first problem, okay? So first of all, this is a ring. What's the radius? This is nominal radius. Mean radius is 10, and the cross section we'll worry about later on. So I'm going to do this problem. Let me save this, by the way. I'm going to kill this job, kill the part, start with the part. Right away, I'm going to save it. File, save management, save as. This is, we're going to make another folder up there, up. The one that I made for this problem was called May 17 Lab 52. No, that's not lab, it's homework, right? So where did I make that? Right here. Oh, no, homework 2, Lab 52. Okay, problem 1. Which lab was this? This should have been Lab 50, Lab 51. That's a mistake. Okay, that's fine. So I'm going to make a problem 1 folder. That was a mistake. Okay, so May 17. No, this is not. Wait a minute. This is for, yeah, that's for next year. Today, the day that I'm doing this thing is May 17th. Okay, May 17th, because today is May 17th, but this is not until, but almost 2 weeks from now. Lab, uh, oh, Lab 52, 51. Okay, Lab 51, that's fine. Okay, right there, terrible. So I'm gonna save it, give it a meaningful name, 1, 2, 3, 4, 5, 6, 7, 8, 9, your student ID number, Timoshenko, your last name, Timoshenko, your last name, and this one is homework 2, problem 1. These are all extra stuff that I'm doing. Okay, so you know which problem you have to submit. Problem 1, it was problem 2 that you have to submit. And I don't know, any other identifier that think is going to be useful, just put it there. Okay, let's go make it. Now, here's the problem. And we agreed that in this problem, I will not do this thing as a wireframe in space. I'm going to draw it as a sketch in the plane. I'm going to draw it as a sketch and then join it, okay? So we go here, Now let's about symmetry. The symmetry, just common sense tells you that this half of this has to be modeled. Okay, just half of it. Okay? So you go there on a convenient plane. On that vertical plane, I will sketch a circle, half a circle of radius 10 inches. Okay, so here, let's do it like this. Let me see, half a circle. Here, let me do it like that. Do it any way you want. You need to have a circle. Okay, good. Let's give it a dimension. This dimension radius is 10 inches. Fit it. There's a fit. Right there. Okay. Yeah, that's pretty much it. Exit. Join it. You need to join because otherwise it won't let you mesh it. Say, oops. Select that. Okay. Sketch one is joined. Apply material to it. Made out of steel, metal, steel. Okay. If necessary and you need to change it, go there, double click on this, analysis. I don't know, in this problem, but you don't have to submit this thing, but I changed, it looks like I've used different values here, so I can change it here if you insist. It's very close to that, 310. Instead of 3, it was 2.9, and this is 0.3. On the test, if you are asked to change. If you are given values that are not what the default values are, otherwise it says default values, so you don't have to worry about it. Say good. Now we're going to save this. Good. So now we're going to go to generative structure analysis. CATIA does not see a solid object. You have to measure it with beam elements right there. You click beam, you select that. If you had not joined, you would not have been able to do this. Say okay. No, I don't remember. Did I use, I don't know, I didn't bother checking the, so there's going to be, I mean, remember this thing was 10, the radius was 10 inches and we are using 0.1 inch size elements. So it's going to be a lot of element, but that's okay. Let's check it out. Right click, mesh visualization, get close. You see that there are very tiny elements there. Okay, for example, right there you can see that this is element 193, which goes between nodes 194 and 195. That's okay. Okay. All right. This is it. So let's save the analysis. File, save management. Here's the analysis. I'm going to use that same kind of thing. Homework 2, problem 1, part 1. Yeah, analysis 1. Save as. Okay, so 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8, 9. Timoshenko, your last name. Timoshenko. This was homework 2. Prob homework 2, lab 51, problem 1, and any other thing that you want to add so that you can see what it is later on, half a circle or something like that. That's good. That's good. Done. So deactivate the mesh. Deactivate. Okay. The top and the bottom are both on planes of symmetry. So let's see. Click on that. This point and that point, let me uncheck that. These are both on plane of symmetry XZ. You see that? XZ. So they don't move in the direction Y, direction 2, and rotations are exactly the opposite. Okay, good. This point also cannot go up or down. So let me go ahead and so that we can easily debug our stuff. So this, I say, right click, properties, I'll call it symmetry condition. Symmetry. Symmetry condition. Okay, condition. Okay, good. This point also cannot go up and down because it is pinned. So another one, I'll put that same point. I'll give it a different name. I say pinned condition, pinned top, pinned top. Say okay. It cannot go up or down. Cannot go up or down. Okay. Now, there's one more thing you need to do, which I'm not going to tell you right now. We're going to run it, and I'll show you that it'll bomb out, and then we come and fix it. Okay. And then this bottom point, you're set that you're going to push it down. So I need a user defined at that point in the direction Z, and I'm going to call it pushing down. Pushing down. Okay. You say okay. Now that we have defined zero value for pushing down, we can go change it. So enforce displacement for this one. And how much, what's the value of the amount that you want to push this thing down by? It says 0.01 inch. Push down by 0.01 inch. So we put down 0.01 inch negative. Good. Now notice that I haven't done anything about the cross-sectional area. So you click on the 1D property, you select this. Because you joined it, you can actually select it. Materials correctly picked. The radius, let me see now, what is the radius here? It says the diameter is 2, radius is 1. Okay, the cross-sectional radius is 1. You say okay, and you can see that there is 1. You say okay. So remember, you do not go and model this as a 3D object. You use the most appropriate element, which is the beam element for this problem. And this is it. The only thing is, if I run it, you will see it bombs out, and you'll see why in just a minute. Okay, so let's run it. And say okay. Say, can you show me what happened? And animate it. This thing can actually spin about that point. In other words, it hinges about that point. If this is a symmetric plate, symmetric, geometry, it cannot spin like that. Okay, it cannot come out of the plane. In other words, let me put it this way: if this was a ring, in principle, it cannot come out of this plane. If this is the hypothetically, if this is Z and this is Y, it cannot come out of the ZY plane. So to take away that rigid body spinning, we have to the easiest way is to say don't spin about Z. Okay, so let me add another restraint so that I can debug it easily. That point, say do not rotate about Z. Fixed rotation about Z. No spinning about Z. You say okay. Let's save it. And now run it. This time it will work, I hope. Oh, something else is happening here. Okay, so let's see. There's something else that I've forgotten to. Let's find out. Let me see. Did it move out of that plane? Oh yeah, it also moved out of that plane. Okay, so I should not let it happen. So this point obviously cannot go up and down because uh, I already did that, or it's right here, pinned, right? Either I can add another one, or I can go to the pin and say don't also move in the direction X. So we can do it like that. So either we go here and add to this direction X, okay? Or you have done another one down here. It says no displacement in direction X. I'll call this thing properties spinning. Stop spinning. Stop spinning. Okay. I'll make a comment at the end. Okay. Let's run it. I guarantee you this time it's going to work. Oh no! What happened now? Let's see. How does it work? Animate. Okay, that's hard to see here with this. So let me change the scale. Let me make this thing, it's this, yeah, it's this bottom that cannot come out of that plane either. So let me do the following. This, you see that? The top is not coming out of that point. The bottom is actually coming out. So let's do this. Let me deactivate this plot. Okay. Down here, I add another restraint there and don't move in direction X. I'm going to shoot myself in the foot if this doesn't work. I think it will. Yes. Okay, so let's first of all change the scale here. Good. Let's look at the view from the front. It's easier to see what's going on. Let's get closer. You can see what happens here. You are applying this thing down. You're applying the force down. You don't know what it is. We're going to find out. But deformation is like this. This comes down because it's symmetric, does not go to the left or to the right. We took away the motion in the direction X so that this comes off the plane. Okay. If you want to look at the displacements, there we are. Double click on it. Average ISO. Needless to say, you push this thing down by 0.01 and the other displacements are zero, so that's why you get exact displacement here. Up there, okay, up there, this is clamped, so pretty much, not clamped, but pinned, so it's all blue. Now, what we did up here, was the equivalent of putting a clamp up there and pushing this thing down. So remember, I did a few changes here to make it work. If you think about it, you have to think about it and concentrate on it. What we did has boiled down to this point being clamped. If it's clamped, it cannot come out of that plane. That's why it would have fixed that other issue too. Now, how much force is needed to do this? So deactivate this. I want to see that. Go there, sensor, right click, create resultant sensor, reaction sensor. Select this restraint that pushing it down right here. Where is that? Not this. Pushing down right there, this user defined, and update, and you're going to get 751 pounds. And if you say, whoa, 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 wait a minute, why is there such a difference between this problem and the other one? Well, these are two different problems. The diameter of the cross section of this is 2 inches. Okay, this is a piece of steel, 2 inches diameter, and I don't know, 10 inches this radius. So we're thinking about a big, fat, bulky object essentially, and that's why you need a lot more force to move it by 0.01 inch. Okay. Now that takes care of this. I don't want you to be discouraged. You have to understand that it's the first time you're seeing these things, and yeah, I mean, you work on these problems, you work on your own, you watch other things, you read other stuff, and you know, you learn it. So don't be discouraged. The first one that I asked to, the first problem, the other problem that I asked to submit didn't require these intricacies, but hey, you're here to learn. All right, guys. Good luck. Now, I do suggest that you also watch the videos from the other sections because those other problems are not the same as what you're doing. So you see, you have a multitude of different problems to look at and learn from. All right. Good luck.